In this session, let us start some DC machines problems. Okay, it's like theory is over. Let us start only. If at all, if we have to learn something, let us learn from the problems only. Okay. Anyway, the first problem is 4-pole lap connected. Active length of armature is 30 centimeters. Diameter of armature is 40 centimeters. Number of conductors are 5 and armature current is 20 amperes. Average flux density is 0.5 Tesla. Calculate power developed and torque developed, speed given. Okay, so in order to calculate power developed, okay, how much is power developed? Power developed equal to EIA. Okay, no losses has been given. So power input, for example, if I think of this as a generator or motor, they did not give. For example, if it is a generator, okay, so generated power into armature current is nothing but output power. Losses they did not give, so that is going to be terminal power, and losses they did not give, that is nothing but mechanical equivalent power. Now IA they have given or not? Yes, 20 amperes. Okay, so what is E? E is nothing but pi Zn by 60 into P by A. In this pi they have given or not? 0.5 Tesla. So from 0.5 Tesla flux density we are supposed to find average flux per pole. What is flux per pole? Is nothing but flux density, average flux density. Actually, like I'm going to about to do one different problem also upon this. Just wait, stay tuned. Okay, so flux density into area. What is area? Means pi d into length. Okay, so pi dl by p. Now you please calculate flux. How much is flux density? 0.5 Tesla into pi into diameter. Diameter of armature is 40 centimeters. So 40 into 10 to the power of minus 2 into length of armature 30 centimeters. 30 centimeters into 10 to the power of minus 2 divided by how many poles are there? 4 poles are there. Okay. So you are going to get flux of 47.2 milliwebers or 0.0472 webers. Now we got pi. Z they have given. What is Z? 500 conductors, and speed they have given 1200 rpm. Number of poles they have given 4, and for lap connected, what do you know? Parallel paths equal to number of poles. Problem solved. So what is E now? E is going to be pi. How much is pi? 0.0472 pi. Z is 500 conductors into N is 1200 rpm by 60 into number of poles equal to 4 divided by parallel paths equal to 4. So calculate voltage here. You are going to get a voltage of 471 volts. Okay. Now calculate power developed and torque. Okay, so how to calculate power? E into IA. So what is power here? Is going to be 471 multiplied by how much is IA? Armature current 20. Okay, so this power is going to be 9.4 kilowatt. So 9.4 kilowatt. Okay, after that what has to be found? Torque. What is torque? Torque multiplied by speed equal to power is nothing but EIA. This is giving noise. Okay, EIA. Yeah, this is somewhat better. Okay, so what is torque here? Torque equal to power is, where is power? 9.4 kilowatt. So 9.4 into 10 to the power of 3 divided by speed 2 pi n by 60. 2 pi into n is 1200 rpm divided by 60. So many Newton meters. How many Newton meters? 75 Newton meters. Problem solved. Okay, now let us think of the second problem. 6-pole DC machine. 6-pole DC machine. Z they have given. Conductor is designed to have 80 amperes current. Now see here. Conductor is designed in the sense IC is 80 amperes. Okay, flux per pole they have given. Speed they have given. Find armature current, induced voltage, developed power, torque if machine is lap connected. Now in this only, like we are going to do wave connected also, and we are going to prove a small conclusion. Okay, so induced voltage, armature current. For example, if it is lap connected, okay, how many parallel paths will be there? 6 pole. lap connected. Number of parallel paths are 6. So 1, 2, 3, 4, 5, 6. 6 parallel paths. Okay, so this is going to be IC, conductor current. This is going to be IA, armature current. Okay, so IC into 6 is going to be IA. Okay, so how much is IA, armature current is going to be? Conductor is designed to have 80 amperes. So 80 into 6, 480 amperes. I think so. Actually, I'm very weak in calculations, I feel. Yes. Okay, now after that, means armature current is over. Let us think of induced voltage. What is induced voltage? Is nothing but pi Zn by 60 into P by A. How much is operating flux? 15 milliwebers. Into how many conductors are there? Z 300. Into speed is how much? 1800. Divided by 60 into, means it is lap connected only, 6 by 6, only one will be there. So if you do this, you are going to get induced voltage of 135 volts. 135 volts. Okay, now what is power? Induced voltage is over, and developed power, EIA. EIA is going to be the power, right? So EIA is going to be 135 into IA 480 is going to be 64.8 kilowatt. Got it, right? So, and after that, torque has to be found. What is torque? Torque is nothing but P multiplied by omega, T into omega equal to power. So what is P? 64.8 kilowatt divided by, what is speed here? 2 pi n by 60. So 2 pi into speed is 1800 they have given, divided by 60, those many Newton meters will come. So what is that? 343. Okay, now let us do the same problem if the machine is wave connected. Okay, so if the machine is wave connected, let us solve the same problem. Okay, now let me extend this to this area. Okay, for example, if it is wave connected, 2 parallel paths will be there. Okay, if 2 parallel paths are there, this is going to be IC, this is going to be IA. Now how much is IA? Is going to be 2 into IC. So 2 into 80 amperes is going to be 160 amperes. Right? Now IA is over. Now let us calculate induced voltage. Induced voltage equal to pi Zn by 60 into P by A. So how much is flux? 15 into 10 to the power of minus 3 into Z is going to be 300 conductors into N is going to be 1800 RPM divided by 60 into number of poles are 6, parallel paths are 2. Okay, so this is going to be induced voltage 3 times of 135. 3 times of 135, 405 volts. 405 volts. Okay, now what happened here? If you observe with lap connected, okay, IC 80 amperes, here current is becoming more. Current is becoming more. How much? 480 amperes. But what about voltage is going to be 135 volts? So voltage is going to be less. So we can think of very less terminal voltage, huge currents, we can use lap connected. And for example, if you think of here, how much is the voltage here? 405 volts. And how much is the current here? Is reduced. Okay, so in order to have more voltage, less currents, we use wave winding. In order to have less voltage, more currents, we use lap winding. That's it. Okay, now if you think of power, power is going to be EIA. So is going to be 405 into IA is 160 equal to, very simple. See, what about the volume of copper you are using in both the machines? Same. So volume of copper is same, means that power handling capacity should be same. Getting my point, right? So current is more here, voltage is less here. Voltage is more here, current is less here. So same power you will get. How much is that power? 64.8 kilowatt. What is torque? Torque is nothing but power multiplied by speed is going to be same. So how much it will be? 343 Newton meters. Okay, in this way we have to solve the problem. Now let us think of about the third problem. In this third problem, this is actually very good problem. Okay, as I told you, sometimes they will give pole arc by pole pitch also, and then they may tell you average flux density, how to solve this problem. It's a beautiful problem. Now 6 pole lap connected generator, 240 coils of 2 tons each, resistance of 0.03 ohms per turn, active length of 50 centimeters, diameter of armature 40, B average 0.6 Tesla. Now focus here. Each pole subtends an angle of 40 mechanical degrees. Okay, 40 degrees mechanical is the crucial point. Okay, anyway, find induced voltage at no load and terminal voltage at full load current of 40 amperes. Beautiful question. Now for example, if I have, okay, this is pole and this is armature. Out of this much area, this is going to be 40 degrees mechanical. This is going to be 40 degrees mechanical. Okay, so my pole shoe is subtends to an angle of 40 degrees mechanical. Now for a two pole structure, mechanical degrees equal to electrical degrees, but for more than two pole structures, always remember one thing, electrical angle will be more. Okay, so if I can convert that 40 degrees into electrical angle, for example, theta in electrical equal to P by 2 into theta mechanical. Okay, actually we are not kids to derive this, to analyze this, such a small funny things. Okay, so because theta electrical should be more, P by 2 will be more if it is more than 2 poles. Now how many poles are there? 6 poles. So this is going to be 6 by 2 into 40 degrees is going to be 120 degrees electrical. Means that out of 180 degrees electrical, this is going to be 120 degrees electrical is going to be my pole shoe area. Now if you observe flux density, now directly you should not take if you take like this, you are going to do a mistake. For example, what is flux? Is going to be flux density into pi d L. Okay, so total pi d L. Okay, so total pi d L is going to be pi d into L will give you the total surface area per pole. If you use this equation, you are going to fail. You are going to commit a mistake, because by saying that, what they are saying, my flat topness, for example, from here to here it is 0 flux density and it is flat topped is the assumption. In the sense, my flux density waveform is like this. Okay, so this is pole area. Okay, so in one pole area of 180 degrees electrical, okay, so 120 degrees electrical you are having this, 120 degrees electrical you are having this. Okay, so 0.6 Tesla flux density is there under the pole shoe only. Apart from pole shoes, you are going to have 0 flux density. Okay, so if I think of this, I should not use this, rather than that into 120 by 180. Getting my point, right? Because in this portion, 0 flux density is there. So let us calculate what is B average. 0.6 into pi. How much is diameter? Actually the diameter 40 centimeters. 40 into 10 to the power of minus 2 into what is length? Actually 50 centimeters. 50 into 10 to the power of minus 2 divided by number of poles 6 into 120 by 180. Is going to be the average flux per pole. So this average flux per pole is going to be 0.0418. 0.0418. Now remaining it's actually very funny thing. Now find induced voltage at no load. How much is induced voltage? Simple. Pi Z N by 60 into P by A. How much is pi? 0.0418 into Z. 240 coils are there. In each coil 2 turns are there. In each turn 2 conductors will be there. What do you say? Okay, because here number of conductors. Okay, how many number of conductors? 240 coils are there. In each coil, 2 turns are there. In each turn, 2 conductors will be there, no, in each turn, into 2. Okay, Z into how much is speed? 6 pole lap conductor, 2 turns each resistance per turn active length, armature conductor, B average, each pole subtends 40 degrees, find induced voltage and load current at the terminal voltage. Pi Zn speed they should have given. Just a minute here. 1200 दिया होगा. Okay. Anyway, because of this, let me tell you one small thing. For example, in synchronous machine, if poles are there, frequency is there, automatically we can find speed of armature, okay, or speed of rotor we can say. But here in DC machine, at any speed it can rotate, so speed should be given by the problem only. Okay, so actually in the problem they have given 1200 rpm is the speed. 1200 rpm is the speed. I'm sorry, I forgot to enter it. So 1200 rpm, 1200 pi Zn by 60 into P by A 6 by 6, because it is lap connected. So this is going to be, my induced voltage is going to be 802 or 202. I think 802. Yeah, 802.56. Okay, 802.56 volts. It can be 202 also because it is not properly printed. Okay, let me calculate. Give me the calci. And meanwhile, let us calculate, IA. How much is IA? They have given full load current of 40 amperes. Okay, so I can calculate power at no load if I want. Anyway, find induced voltage at no load is done, and the terminal voltage at full load current. Okay, so we have to calculate what is terminal voltage. If this is a generator, in generator, induced voltage will be there, resistance will be there. Okay, so if I think of induced voltage is EG, current is going to be IA, and this is going to be RA. Okay, now if I calculate, okay, let me calculate this 0.0418 into 240 into 4 into divided by 60. Yes dear, 802.56. Okay, it's good. Now anyway, if I want to calculate terminal voltage VT, EG minus IRA, because it's a generator. Now IA value I know. How much is that? 40 amperes. Now armature resistance has to be found. Okay, so in order to find armature resistance, let me use this place. Okay, so armature resistance has to be found. Okay, how to find armature resistance? Resistance per turn is 0.03 ohm. Okay, so resistance per turn is 0.03 ohm. Now how many coils are there? 2 coils, 240 coils of 2 turns each, and each turn is having this. So total resistance if I calculate, okay, total resistance if I calculate is going to be per turn into 2 turns in a coil into 240. Okay, so this is going to be, let me calculate, that's better, 240 480 into 0.03, 14.4 ohms. For example, if I think of a wire, okay, so if I think of a wire like this, if this wire resistance is 14.4 ohms, okay, so out of this, for example, if I cut this into half. Now each is going to be, for example, from here to here, if it is R, this section is going to be R by 2. And now if I connect this R by 2 in parallel, so R by 2 is going to be R by 4. What do you say? Okay, very simple. If I have this length of resistance as R, half is going to be R by 2. This is going to be R by 2. If I connect these two in parallel, R by 4. Now let us think of our machine winding. Okay, so in this winding 6 poles are there, lap connected. So how many are there? 1 2 3 4 5 6. Okay, now if I connect these all these resistances in series, 14.4. now each resistance should be like 6 parts are there, 14 by 6, 14.4 by 6 ohm each. Okay, 14.4 by 6 each, so such that if I connect all these in series, it's going to be 14.4. Now how much is this total equivalent resistance here? It means if equal resistances of n resistors are connected in parallel, net equivalent is going to be 1 by n. So this is going to be 14.4 ohms by 6 each resistance. Such a resistance are 6 are there into 1 by 6. So this is going to be 14.4 divided by 36, 0.4 ohms. Okay, 0.4 ohms. Now RA equal to 0.5, 0.4. Okay, now how much is terminal voltage? Terminal voltage equal to EG, how much we got? 802.56 minus IA is how much? 40 amperes into 0.4 is going to be 16. Okay, so 802.56 minus 786.56 volts. Okay, so actually one thing we have to understand here, the conclusion is very simple. In the first problem, okay, what is given? Average flux density of 0.5 Tesla is given. Okay, in the first problem, average flux density of 0.5 Tesla is given, and pole subtension they did not give. So we have to assume that my flux density is like this. This is 180 degrees. 180 degrees electrical. Okay, such that what is this average flux density? Here they have given 0.5 Tesla. Now in the third problem, whatever they have, what they have given, they have given 0.6 Tesla, but they have shown that, for example, like this. So this is 180, but up to 120 degrees only. Up to 120 degrees only, it is 0.6 Tesla. Okay, so if you can understand this, we can do better in gate.